So in this video, I'm going to continue with capacitance. We'll solve some more problems. So in this question, we've got a circuit with one capacitor here in series and then these two in parallel. You're supposed to find the total capacitance. In order for me to do this, I have to break it down. I'll figure out this part first, then I'll figure out the overall thing. So if you remember the rules for capacitors in parallel, that's easy. You just add them. So that just becomes 2C. Now that we've got 2C, we also have this one in series. If you remember the rule for C in series, this is going to give me the final answer now, I will have to do 1 over C plus 1 over 2C. This can be done like this, in a little bracket, the -1, and in your calculator, all you need to do to just double check the fraction, just consider C as 1. So I can just literally do it in my calculator, 1 over 1 plus 1 over 2. And to the power of -1, that'll give you 2/3, 2 over 3. So you can bring the C back in again, 2 over 3C. Which option is similar to 2 over 3C? It's 2C over 3. It's the same thing. I multiply by the 2, but I divide by the 3. So this is the same way as this. Okay. Over here, this is actually quite a big question in a multiple choice format. So if you're unlucky to come across this, I'll help you on how to figure this out. The idea is you have two capacitors separately charged. Then they're connected to each other. Positive connected to the negative. That part's important. Then you need to find the final charge. So the charge will be redistributed. The only way we can do this, first of all, is figure out what the starting charges actually were. So if I wanted to do that, I'll take both of these and I'll do Q equals CV on both of them. I'll do Q equals CV for the first one, so I'll call that Q1. I'm going to do that right now. C and V, so this is 1.5 or 1.50, you don't need the 0, multiplied by 40. I'm just going to keep it in micro because the final answer is in micro, so I don't need to write times 10 to the -6. So if I was to do 1.5 times 40, I would get 60. So this can be 60 microcoulombs. Q2, I will quickly check now as well. Let's find out. 2.40 times 15. 2.4, this is Q2 now. Multiply that by 15. Once I've done that, I will get the answer. 2.4 times 15 is 36. 36 microcoulombs. So this is the total charge I have on each capacitor before I connect them. Now I'm going to connect them. How? It said one will be a positive side and one will be the negative, and I will connect them to each other. So I can draw it like this, and this negative is connected to the positive. And then minus. Okay, so what does that mean? Originally I had 60 here and I had 36 down here. So now what's actually happened is because it's the plus and the minus, the charges are able to move. They can redistribute. They cancel each other out. Similar to something that we did in the first topic, topic 1. If you remember the two spheres, we had the two spheres, and then what happened? They touched. And then when they touch, then you separate them, the charge was redistributed. The same idea is here, the charge is redistributed. Now, because it's plus and minus, what I'm going to do is find the total charge. So in order for me to do that, in this case, I will have to do the 60 minus 36. And that will give me the answer, 60 minus 36 is 24 microcoulombs. Why is minus? Because the charges that were already here went back this way and to cancel out some of the charges on that side. So you subtracted. However, if I connected the positive to the positive and the negative to the negative, that would be the opposite. They would repel even more. More charges will repel. In that case, you would add the two together. But in this case, we are not doing positive with positive, it's positive with negative, which basically means that they will redistribute. You will cancel some of the charges. Another way to remember it is when we did the Q inner and Q outer of a ring, when we had a charge inside. The inner here and then the outer here, they redistributed. Again, let's not get into that. We have now figured out the total charge. Now I know the total charge, I can get closer to my step. I need to know what the voltage will be. since they're connected to each other, they're kind of in parallel. So if I was to place a voltmeter here, like a V, if I was to place that, it's going to place it across both of them. So I can quickly find the V by doing the Q that I've just found over the C, the C total. So this is the V total, and being parallel, I can use this to help me get the Q on each capacitor. This is the steps that I'm going to take. Q is 24, and I'm going to divide that by the C. Now there are two C's in parallel, easy to add. You just add the two numbers together. You'll have 1.5 plus 2.4. 2.4, that's a 4. And that will give me the voltage here. So let's quickly write that out. I've got 24 divided by, in a bracket, 1.5 plus 2.4, and I should get an answer of 6.15. 6.15. So the new voltage, after they've been connected together, becomes 6.15. Now I know this, I can find Q on any charge, Q equals CV. So now I can do it. It's asked me for the 1.51. So what I'm going to do is I'm going to do Q equals CV. I'll bring that down here. I'll do Q equals CV. I'll take my 6.15 and I'll multiply by that C. 1.5 multiplied by 6.15. If I do that, 1.5 times 6.15, I should get 9.23. 9.23 microcoulombs. That is the Q on this charge after on this capacitor after they're connected together. So the answer is C. Kind of just blocked it a little, but that's the answer there, C. Okay, so a few steps were needed. Now, we've got another circuit here. We have this is in series with these two. Again, if you want more further details, refer back to my other video when I solve a big circuit question. So what I'll do is, assuming that you have seen that, I'll be able to continue with this one fairly quickly. So I'll just get that out of the way, save some space. Okay, so if I wanted to solve this, I'm asked to find the charge in this one here, in C3. In order for me to do that, first of all, I need to know the total capacitance, so I can find the total charge. So then I can find the voltage, then I can find the charge stored. So a few steps is required. So the first thing I'm going to do is let's just quickly figure out the total capacitance, shall we? Let's do that now. Here we go. What we have is we have these two in parallel plus series with this one. So C2 is 6 microfarads, and I'm going to keep it in micro because this is in micro, and this is 3 microfarads. C1 and C2 are actually 6, so that is also 6. Okay, so what I'm going to do here now is I'm going to figure this out by just doing the 6 plus 3. This is total of 9 microfarads. That's the final one there, 9. And then I have C1. I will do 1 over 6 plus, the mouse turned into a pencil finally, 1 over 9, and I'm going to do that to the minus 1. That will tell me the total capacitance. 1 over 6 plus 1 over 9, what does that give you? Let's find out. So I'm going to open my bracket. I'll do 1 over 6 plus 1 over 9. Close the bracket to the power of minus 1. Directly the calculator gives me an answer of 3.6 microfarads. That is the total capacitance. Now I can find the total charge. Q total equals CV. 3.6 that I've just found, multiply that by the battery, which we have is 10, which is going to give me 36 microcoulombs. Now that I have figured out the total charge, I can find the individual charge here if I know the voltage across this. These two do have the same, just like above, they're parallel, they're the same voltage, but they're sharing it with C1. So there are two ways I can figure it out. I can calculate the C1, the charge on C1, and then subtract it from 10, or I can directly go ahead and calculate it from here. I've shown both ways in my other video. Sorry that I keep referring to it, it's just I don't want to make this one longer than it has to be. So I can find the voltage over here. This is the voltage in the parallel section, will be my Q over C. So the total charge coming in is going to be 36. It comes in and out. 36 is the total charge. It's split, but I don't know how much. It does not matter. The total charge is 36. running out of space, equals 36 micro divided by the parallel capacitance, which I've already done. And 36 divided by 9, 36 divided by 9, of course, is 4. That is nice times tables there. Don't know why I use my calculator, but anyway, that is 4 volts. Fine. Now I have 4 volts. I can find the charge on any capacitor in these two. Let's find the charge on the one it asked me for, which is C3. So, continuing from this, Q equals CV, specifically C3, C3 being 3 micro, multiply that by 4, 3 micro times 4, of course 3 times 4 is 12 micro. The final answer in this case will now be 12 microcoulombs, which is B. Okay, very easy. It takes a few steps, but it's not difficult. All right, so moving on to the next question. This is pretty much the same as this. The idea is exactly the same, which is showing you a little bit different. You have this one in series with these two. So for this, just refer to the solution over here, and the answer is the same, 2C over 3, which is the same way. The capacitance of this is here. When the voltage is this, what is the energy stored? So we have a C and we have a V. So thinking about the 3 capacitor formulas that you have written on the formula sheet, I know that I can use the energy formula, which is a half CV squared. A half times 6 times 47. I should actually have said half times 47 times 6 squared. V is 6 and we square it. And you get your final answer of 846 microjoule. This is direct substitution, nothing crazy here. Alright, so I'm going to erase this so I can make space. There we go. When a capacitor has a charge of this on each plate, that means on each side you don't need to do anything extra, but it says that potential difference is 10. Then we change it. We want to know how much energy is stored when I change it to 120. So the idea here is I can only find the energy stored if I have like one variable that is being changed. I'm changing the V over here, which means the Q will also change. So I cannot just simply use V is Q over C. It's not going to help me. All right. Well, actually, that's what I can do. I need to find the C. If I can find the C, I can actually solve this. Let's see. Let's find C equals Q over V. If I can find that, Q over V, then I can use one of the capacitance formulas again, maybe the same one above here. Let's see what happens. C is Q over V. 80 micro divided by 10, which is going to just give me, 8, isn't it? 8 microfarads. Once I've figured that out, I know the capacitance is going to be constant, 8. The capacitance won't change. I can now figure out what does it ask for? Energy. Energy stored. I have a new V, so I can just do a half CV squared. A half times the capacitance, which we figured out is 8 micro. I'll just write micro rather than times 10 to the minus 6. 8 microfarads. Multiply that by 120. Running out of space again. 120 squared. I need to really think this through. 120 squared. If I put that, and yes, I will get my answer. 0.0058. I'll get 58 microjoules. Amazing. All right, so not microjoules, sorry, it becomes millijoules. All right, so how much energy is stored when you have this? Again, it's just direct substitution, isn't it? You have your C, you have your V, and it just happens to be the same formula as above. U equals a half CV squared. This is my C, this is my V, checking them. If you remember the formulas, you have U equals a half QV, and then you also have a half CV squared, and you also have a half Q squared over C. So these are the rules that we can use. So anyway, we've picked this one here more than once now. Solving that, you'll get 8.10 joules. Okay. So there's a couple of more. The rest of these have just been cancelled, so I'm going to ignore them. I'll just quickly do these two, and then we'll be done with this lesson. A capacitor stores this when it holds this charge. The same capacitor stores this when it holds that charge. Okay, what is the ratio of the energy stored? So when it comes to energy, we're comparing it with this Q. So what we're going to do is when we have this, if you think about the rule for the C and the Q, the C is the same, so that's a constant, which means I can use a one of the formulas from before, we're changing the Q across. So are we changing the voltage? No, it does not look like we are changing the voltage, so that's fine. I can think of this formula as U equals a half Q squared over, what was it? Q squared over C, because C stays constant. So I know I can keep this one, and I'm going to use the Q because that's the thing that's being changed, okay? I can't use the other ones because I cannot tell whether the V is the same or the V is changed. So this is the one that I have to use because this remains constant, and this is the thing that is varying, okay? So look at that, Q squared. You can kind of guess where this is about to go. To compare the two, if I make this 16 times stronger, if I just use the formula, I can just literally just do 16 squared. If I make it 16 times stronger, that is 256. So the ratio of the two of them, well, because of the Q being squared, it becomes 256. That's the energy, comparing the energies, 256 times, basically because it's just squared. Now, the final question here. Two identical capacitors, they're in series or in parallel. How should they be connected to get the smallest capacitance or the maximum energy? So, if you remember, capacitors in series gets smaller. So, C and D are out. And if you want to get most energy, it means you need to have more space, as in more capacitance, then you can store more energy. So that means it should be parallel. So A is also out. So that means B is the best answer. In series, the capacitance is a lot weaker because the distance between these two plates, the far end plates, are very, very far away. In parallel, it is a bit different because you have more paths to travel through. The electrons can go over here. When it becomes full, they'll go over here. You have created a bigger surface area. So it comes kind of from the formula C equals epsilon A over D. Not so important. There you go. You have your answer. And I will stop there. Thank you.